Ready.
Great. So last time we met, we were talking about some other ways to find the most important features we wanted. And I added some things that I thought you guys would find useful. And I will restart this notebook so we can go from the beginning. Excuse me a minute.
Make sure you read your chin guards.
Okay, so where did that go?
Did you share this notebook with us, Tom?
Yeah, I'll make sure the link is shared in the pipeline chat.
Okay.
But it'd be better to watch it for right now.
Okay.
Okay. So here I'm just importing NumPy, and I'm using our common method of just creating some random features. And so I'm going to create 3 of them. And notice that I'm making them all between 1
Are you sharing, Tom?
I don't think you shared your screen yet.
My bad.
It's okay.
That must be it. My bad. Sorry, guys. And y'all will have to help me because Linux acts just a little differently with the grid view on the people in when I'm presenting to. So, okay, here we go. We're importing NumPy, so we can import NumPy random and then uniform distribution. We're going between 1 and 51. We're going to get 100 values of each. We're reshaping it to a column matrix or a column vector, really. And then this is what we're pretending we don't know, the actual model. Of course, we want to know it too, because we want to make sure we can recapture these weights. And notice that I'm purposefully making the last weight really small. Now, I'm doing this for convenience because I'm trying to focus on a specific thing. In reality, we would want to scale all of these features, but since they're all within the same range, we've already kind of pre-scaled them the way we've created the features. Again, this is one of the values of creating fake data, because then we can create it just like we need it so we can focus on the thing we're trying to learn. And then I'll stack those all as one group of X. Now, next, I'm going to use our power. And by the way, Geith will be showing how to do this with logistic regression, or he's going to be doing the classification type stuff. And if for some reason one of us is going to do it, but we're just focusing on the regression today. So we import some metrics. I'll show you the one we're going to use. We import linear regression, but again, we're just using it as a tool, not to create our final model or anything. We're using it to help us figure out what features we would want to keep. Now, I should point out, we would have wanted to look at a correlation matrix before we do this. Why? To see if we have any collinearity problems. And then you've already seen that we did something like this to figure out which feature among collinear features do we want to keep. But this is another trick. Once we know we don't have any collinear features, we just want to do a Pareto. Now, of course, one way to do the Pareto is just to figure out the feature weights. And we know we should get 2, 3, and 0.01. So this would be the most important feature, the second most important feature. And this one's almost not even worth using, right? So what am I doing in here? I have this array that I call in build, meaning it's in the build array. I am building this array up of indices that I want to keep. And as I do that, I'm saying for M in range 3, and then down here for I in range 3. So that means I'm going to loop through all of my features. But then after I loop through all of them, I'm going to loop through that many features again. Notice I'm initializing an R2 max, meaning R squared. R squared is a specific type of metric that measures the goodness of fit, or the goodness of fit of a regression model, but also in the sense of which one minimizes the error the best. It really is good metric for that. And then I'm looking for the max index among the features because I put them all in this group. So that will get reset every time I go through this loop. So each time I'm looking for the IMAX that I'm going to add, say that was the best feature to improve this model. And so now I have a special case here where if m equals 0, I make xtrain this way because it's the first vector. But if m is greater than 0, I've been building up. So I have a special array called xbuild that we'll cover here in a minute, and that will be covered after this first one. And then I'm adding each one at a time through this loop to see, okay, if I add another one in there, I do the modeling. So I just initialize a model. And you know what, I'm going to take this out. We don't need copy equal false. That's just been an artifact that's carried forward in our work. And then we do the fit, we do the prediction, and we use the Y that we created up here, right here, and the Y predict that we just predicted with the model, and we get an R squared score. Now, again, this came from here, the scikit-learn metrics class or module, and we're calling the R2 score. And if any of you want, I'll develop a special markdown cell that goes through the math of this, but it might be good for you to look that one up on your own. It's not hard, it makes sense, but you kind of need to think through the elements of the equation. Then we're looking for the current R squared greater than R squared max. Now, of course, it'll get changed right away because I made this super ridiculously horrible R2 score that could never be calculated. So the first time it gets replaced. And so R2 max gets set to that first one and I max to that one, but only when R squared gets better will it replace it this time. Now, once it's done, this figured out the max one through this part, it adds that I max to this in build, meaning it's in the built set of features that we're building back up. And this is just a reporting version here. I'm just saying, oh, I don't want to use program numbering. I want to use the other numbering. Then I just do a little report here. In build equals that. So it shows me how it's being built back up. And when the in build is, when this feature xi max is added, R squared is this value. And then if m equals 0, it initiates the build. And that's just going to be the first maximum feature to give the max R squared score that we found. And then we do this important reshape so that scikit-learn will be happy. But if m's greater than 0, we're using the NumPy HStack feature, where we just add this latest maximum feature to this. Now up here, this is really important right here. If we're looking at a feature in this loop, if it's already in the in build, we're gonna, if that I is in the array we're building slowly, we continue. We're only gonna look at ones we haven't added on yet. Now, like anything, when you're looking at someone else's code, if there's something you've missed here, you can ask now, but what's always the best thing to do? Break this into little piece by piece. For example, I could just start playing with this like this. I just highlighted everything. I hit Control/ to comment all of that out, and I could just see how much this does. And then I could go and just make sure I can break this up into little pieces. I could add another code cell here so I could run piece parts of this. But the key is be insistent with yourself. Take a good pace. If there's something here that confuses you a little bit, take it into a smaller environment, like another cell or your integrated development environment like VS Code or whatever you use, and just study what it does in isolation until you understand it. And then go to the next step you don't understand. But again, at a very high level, in this loop, I'm just looking for what feature gives me that max increase in model accuracy. That's all that loop's doing. And I'm just looking to add the strongest feature. But the next time I go through it, the next time I go through the outer loop, I'm resetting these R2 maxes, and I've added that feature index to this in build so that it will be skipped the next time around. And that way I'm adding the second most or the third most, etc. And this could work for hundreds of features, but we're just showing it for this small one. And you can see already what it's going to do. It says, well, in build equals 2. And again, remember, this is not programming indexes, it's human indexes. And when X2 is added, R2 goes to 0.45, all on its own. That's great. But that's with just one feature. The next time it goes through, it's skipping looking at 2 because it's already in there, and it's using 2. When it used 2 and 1, in other words, feature 2 and feature 1, well, when X1 was added, it jumped the whole R squared score up to 0.9999. Now, at this point, we realize, oh, shoot, when we add that very last feature, I could probably get away with dropping X3. And we kind of already knew that was true because in our fake data prophecy, we made it that way. So that's when we add one feature at a time and see how it's affecting model accuracy. And we obviously want to get close to 1 or at 1, but usually it's close to 1. But what if we removed the least important feature, then the next least important feature each time? So we're going the other way. We start with all the features and we remove one at a time. So this gets just a little trickier. First, I just say, well, if I'm going to remove them, I want to compare that to when I have all of them. So I run this first. And it will report 1.0 like we expected. Oh, and note, I'm not adding any fake noise. Why? Just to keep this simpler for the topic at hand. But in reality, your data is probably going to have noise. Okay. So instead of calling in build, I call it in left. In other words, not left as in the side, but left and how many do we have left? So at first, it's all of them. And then what's been deleted too. I want to track that. And this was just something I used during development. And then I'm going to call X build. I'm going to make it a copy of X because I'm going to affect that one. Now I do the same thing again. I'm wondering, hey, as I remove each feature, which score is the max? And of course, as I do that, I'm going to expect that it's going to remove X3 first. But in this, so this is the outer loop where I go through, I've already looked at the case with all of them. So now I'm looking at the number of features minus 1. And so now for what I have in the first case, I'm just going to remove the one that maintains the max. If I remove each one systematically, which one is going to give me the max R2? And so I've commented out these print statements because I was using them to help me troubleshoot when I built this. But temp build is a copy of what's left. And then I look for it when I'm trying this out, I say index temp build pop I, meaning I'm I'm creating a copy of what's left. And right now it's everything. I'm going to pop them one at a time, meaning take them out of the array and find out, well, what index, because it's an array of indices, what index did I pop? And then I'm going to call, I have this temp build. And oh, by the way, when I did this pop, temp build has that indice removed right now. So Xtrain for right now is a reduced version of the features, but it's removing one feature at a time. Then for each of those times, it does a modeling. By the way, depending on the size of your model, this could get expensive, but it may be worth it too, depending on the approach you're taking. Personally, I like the p-values. And then I do a score, just like I was doing before. And then I'll find the Imax this way. And so in left will pop Imax. And that way I'm saying, well, the one that resulted, as I did each removal, the one that left the maximum value was the least important one, because we're going from least important to most important. Let me make sure I labeled that way. Yeah. And then I'm keeping track of what I've deleted too. And then this is just a reporting. It's a uppercase version of that. So now I'm just adding one to it again. So it's human numbered, not program numbered. And then I do a report on that to see as I remove each one. So let's run that. And it's the same thing we already saw with all features 1.0. But the ones that are left are 1 and 2 because I removed X3, and wow, I still have that high number. And so I can discern that X3 was not very important, even going this direction. And then I find that 2 was the most important. It was the last one to go because it was the most important. Okay, well, that's kind of expensive. What if there's another way that wouldn't require as much looping when I have a lot of features? So let's recreate our features, but let's make the X3 coefficient smaller. And let's stack all our features together again. Now, what am I doing here? I'm importing the scikit-learn metrics package again. I'm importing a version of linear regression called Lasso. Now, picture what linear regression is trying to do. And I realized just now, probably would have been better had I showed this mathematically, but bear with me. In linear regression, the model looks like this, right? Well, I guess I can do it just right here. I'll just say plus an L1 norm of what? Of the coefficients. Now this is just text. Well, what would the L1 norm of the coefficients be? It'd be 2 plus 3 plus 0.001 and the absolute value of that. Well, now when you use Lasso, you're literally solving for y, but with this term in it, the L1 norm of the coefficients. And how do you spell that? I think that's right. I can't remember now, but the coefficients. Yeah, did it there too. Okay, good. That's how simple it is. This is a penalty term hanging out here. And it's just saying, I want to drive this. Now, again, remember, we don't know this ahead of time. We do, but normally you don't. We're just studying to see what can be done. Well, I'm going to set up my model. I'm going to do a fit. I'm just going to look at the regular linear regression because I've imported both of these. But then I'm going to go through all these alpha variable or values. 0.01, 0.1, all the way up to 40. I'm going to see where does lasso start to really drive those small feature weights to 0? So lasso is just like linear regression, but adding this L1 norm to the end of it. No big deal, but boy, hey, and the guy that figured this out is still alive. Before this, there's another version of this called Ridge. So let's do this. We'll call this lasso. And the other version would be plus L2 norm. And it's also of the coefs. I'll just do it that way this time. But the L2 norm is the Euclidean norm. We would square each of those coefficients and then take the square root of them. But we're just gonna, since they're so similar and they both use a weight term, like this alpha that I'm calling alpha, that we can change, it's a hyperparameter. I'm just gonna call it, just gonna use lasso because they work the same way. Now there's one other method called elastinet. And it is a combination. It's some alpha times L1 plus some beta, which alpha and beta can be whatever you want to set them to, L2. Okay, so those are the two types. We call these methods of regularization: lasso, ridge, and elastinet. But we're just looking at lasso because they all work very similar. So now to distinguish it, I'm calling this the lasso model. And I'm going to do a fit with everything. But notice this is the advantage. This is simpler to code, and it's a little less expensive, frankly, time-wise and coding-wise both. So then I do my Y prediction with that lasso model. And I do the R squared score. And then at the end, I'm going to take the one that was the smallest, and I could automate this, but I've just done it manually. I'm just using the first two features to do yet another model to see how it compares. Okay, so just to make sure, I'll rerun these. I think I already did run them. And we'll see how this does. So yes, this is like we expected. It's 2, 3, and 0.001. Excuse me. Now we can look at these weights, and we should point out that I'm predicting with my training data. It's because I'm not doing model prediction yet. I'm using modeling to help me figure out what coefficients I want to keep. So we haven't really formally talked about train test split yet. That's a very important thing to do, but you don't have to do it when you're doing feature reduction or other things in the pipeline before you get to the official modeling. We're just using modeling to help us make decisions. So you can see there's very little difference on these first two when alpha was set to 0.01 and to 0.1. But when alpha is 1.0, it starts to make a little bit of difference. And when it's set to 10, it drove that unimportant feature to 0. And then of course the higher ones too. So if you're using lasso more for finding what features you can drop, this is an indication you might want to set alpha high. If you're using it more for generalization, you might want to set alpha closer to 1. But when I remove X3, look at this, I still get great predictability and probably have generalized well. In fact, this feature was just probably not important. So let's review what we've covered. We finished up a little bit more on how to reduce features. And the first thing we went through was adding one feature at a time, but making sure the one we add is the most important. Once that one's there, to accuracy of the model, that is. Once that one's there, we look for the second most important, etc. Here we start with all the features and we remove one at a time. And then here we use lasso. Now, when you're actually using regularization techniques like lasso, ridge, or elastinet, to generalize a model, that's when you're not intending to remove a feature. But when you want to find out what features to remove, lasso is really the only one I would recommend using in that case. And notice I used lasso to figure out which feature was least important, which one I could drive to 0 as I raised alpha, but then I made sure it looked good with that. It might have been a list of unimportant features, by the way. It may have been more than one of these. We've made a very simple fake model, but you can see that, wow, this is great. This is probably going to have better parsimony, better generalization. Okay, before I move on, are there any questions on that? And I'll make, this is already in the course Google Drive. This fake and continuous classification project steps, which is here, which is shared. So I'm going to just put this real quick in our chat. There we go. Excellent. Thanks, Minha. I always love it when you add stuff. It drives them to 0 more directly than Ridge would too, right? Okay, I've got the chat open now. That's good. And that's just in case y'all didn't already have that link. It hasn't changed or anything. Okay, let me go back to that. Okay, I don't sense any questions, but correct me if I'm wrong. Now I'd like to go over to the simple iris data set and talk about, this is a whole new animal now. We're shifting gears completely. We did polynomial features last week to show how to do feature engineering. We talked about other aspects of feature engineering. When we start talking about principal component analysis, we're talking about a whole new animal. We're talking about a whole new thing. Now, before we get into it, let's talk at a high level about something. If I multiply one matrix by another matrix, think about, what am I really doing? Matrix 1 is being transformed by matrix 2. It's literally a transformation from one space to another. Matrix 2 is forcing a spatial change to matrix 1 such that the resultant is a new perspective. Now, in that general spirit of linear algebra, when we do matrix multiplication, oh, by the way, in case that's just a big revelation to y'all, let me get put in a plug for learn everything you can from everyone and everything. Why was I able to share that with y'all? Well, Saul Kahn teaches it when he's teaching your linear algebra, but also I saw it firsthand when I was doing robotics. We're constantly doing, when we have a string of what we call T matrices that represents the robotic model, there can be hundreds of them in a robot model, or 30, let's say. For each transformation, it's a matrix. And so roboticists are always thinking about matrices, like you start at the matrix that represents the ground, and then you travel through the robot. And by the time you get to the end, you've done that last multiplication, it has transformed this over to the end point of the robot. So even if you're in some other type of unit system or some other type of physics, it's still a transformation in that space. And so hopefully that gives you some insights. But what is principal component analysis? It's the job of finding a matrix that will transform the first matrix into this magical space where all the features are completely decoupled from one another. And it was essential to know how to do this for both, well, not so much for robotics, although we did it there, but especially vibrations analysis. Why? Because we needed to know the individual modes of vibration. And what did the eigenvectors tell you when we found them? We had to do these by hand, by the way. Although we did have programs even back in my day, my graduate school days, to do this. For tests and stuff and homework assignments, we did smaller problems by hand. Each eigenvector, if used, and you could scale the vector, but if you just used it as a unit vector and plugged it in for your initial conditions and simulated your system, it would excite only one mode of vibration. I thought that was so cool. It just basically was telling you each effect, but it was a mixture of the original state variables. Just like we've seen here, when we go into eigenspace through the eigenvectors, which the eigenvectors form an eigenmatrix, it's literally transforming us to this magical space where everything's decoupled, but there's special mathematical techniques to figure out those eigenvectors. And then each eigenvector has an associated eigenvalue. And the importance of that feature in eigenspace is dictated by the eigenvalue size. But please understand this. If you do not scale your vectors, the eigenanalysis for figuring out which eigen features are most important will be lost on you. It'll be conflicted information-wise because it's just going to go with the original space vectors that were the biggest magnitude, or when you get into eigenspace, the one that had the biggest combination of original space features will have the largest eigenvalue. So you really want to scale to keep things on even playing field. Now, I've been saying that a lot lately, but I want to go test it because I had a slight doubt as I was saying it. But how do we do this? Let's just step through it. Well, we want to do standard scalar, and we're just going to get a simple data set. And what are we going to do? We've already, let's see. Looks like I needed to, I think something is not loaded here. Is that going to even work? I just am having a doubt because, yeah, I need to import decomposition. So somehow I failed to put that in here. I thought I'd run this before. Jonathan and Minha, can you help me search for what, let's see, scikit-learn, I'm pretty sure, decomposition library. And then we're going to need to do PCA, I see it there, PCA eigenvalues.
Yeah, most likely SciPy or scikit-learn, one of those two.
Yeah, so I've got it now. We just need to import, it's called, just like you would expect from looking at what we're seeing here. I'm going to change it just a little bit. We're going to do from sklearn decomposition, import PCA. I don't normally like to do it this way, but I'm going to just do it this way for time. PCA, it is uppercase.
Yeah, that should do.
And then we'll, there we go. And we're saying number of components equal 4. And boom. So what's going on here again? We scaled our feature variables that came from the IRIS data set. We did we initialized, instantiated a PCA class. We did a fit transform on it, so we got the eigen features directly. So the shape of X in eigenspace is xe.shape. The eigenvectors are, etc. But we need to, this is just to transpose them so they do represent the eigenvectors. In other words, column-wise. And then explained variance. That's going to be the eigenvalues themselves. And then what I'm doing here is simply doing a scaling that a percentage-wise of importance, basically. So all of these will add up to 100%. And then compare the first values of XE and X transpose. So this is just to make sure, as I go back and forth using the transformation of the eigen, I like to call it the eigen matrix. It's all the eigenvectors concatenated together. We're just making sure that that as we do the transformation back and forth, one direction back to the other, that it works properly. So that's all that was happening there. There's a lot going on under the hood, though, and I wouldn't get you to work. Notice I stepped through a lot of math. I didn't this time. It's been a couple of decades or more since I've done this math by hand too. But the shape of X in the original space is 150 by 4. So there's 150 data points, but they have 4 features. And the shape of X in the eigenspace is the same. And here are our eigenvectors. It's 4 by 4. And here we can see that we probably could just use the first 2 eigenfeatures. But that doesn't mean that we would therefore say that, oh, then we don't need as many original space features. No, this is a different space now. If we took these 2 eigenfeatures away and transformed back to the original space, we'd find that we still had 4 features in original space. This is different. This is eigenspace. And again, let me point out, I was just looking at their percentage weight-wise. So as I look at it this way, it's more insightful because I realize, oh, I feel for myself, I feel comfortable removing this one. But 3%, almost 4%, yeah, I'd like to keep that one. And then I just made sure I understood from using the eigen matrix that I could transform back and forth between the 2 spaces. And you see, that's all I'm doing here is doing matrix multiplications, where again, it's transforming from original space to eigenspace and eigenspace back to original space, or vice versa. But that's all fine and dandy. What I was saying, what about a bigger data set that might show us more about what I was saying about the before and after? Well, this is the diamond data set from Kaggle. I believe it is from Kaggle. And let me open up the outline. And I'm not going to rerun this one, but this is original space first. So I'm just saying, I'm doing, excuse me, no, I'm speaking incorrectly. I'm looking at yeah, I'm looking at the original space features here in this map here. So that this is the data from the scaled vectors. Boy, I thought I reviewed this carefully, forgive me. Oh, there's more. What is, oh, there we go. I was looking at the bottom, my bad. Okay, so the diamond data set. What I'm going to do is load everything here. And then these are the column names for the data set. And I'm reading in this data set. Now let me make sure in files. Oh dear. Let's see if I can get to these. I think to avoid problems, we'll pretend that I ran this because it is saving the last output. I need to make sure I can get to diamonds. And I will make sure diamonds is in, maybe it is. I'll make sure I add this diamonds data set in this directory so you guys can load it and play with it. So I'll do that after mentoring today. So I'm going to load that into a pandas data frame. I'm going to name the columns, and then I'm going to do some text, encoding of text to numbers. So this is ordinal. This is also ordinal, and they're all ordinal. So using some diamond domain expertise help, we're able to transform these to ordinal values. And then we do the scaling in those two lines. Then we create a data frame from the scaled values. Why? Just so that I can do this correlation matrix using the pandas version of it, because it's kind of nice. And then I create my heat map. And oh, wow, we've got a lot of collinearity happening down here. And it may be that, wow, there's some reason maybe I don't want to get rid of that collinearity. So what do? I'm limited to PCA. So I go through PCA and I do the fit for PCA and the transform, and I've got my PCA data now. And I do these reports down here, and then I turn it into a plot. And I'm looking at the cumulative going up to 1. You can see right away, boy, we really probably don't need 6, 7, and 8. But just to show you, if I remove those, okay, great. Look, I get a very, I could have printed the matrix before I remove those, but if we don't remove them, we still see it all decoupled like this. All these values would be very small, showing us we're very far from any type of collinearity. But when I return to the original space, look, I still have the collinearity and it's stronger than ever. Wow. So that's just to point out, there's a burden of explanation to say, okay, I'm in eigenspace and I'm feeding the eigen features to my model, but now how do I do explainable AI? How do I report back to the stakeholders, we're doing this model, but the features going into the model are this? Well, again, you can use a different model for explaining things than the one you use in production. All the techniques we've done up till now before PCA could still be done. It just may be that you get better predictive results with PCA, but you might also want to say the predictive models leaning on these PCA features or eigen features, and here's how each of those features relate to respective original space features. And as a special treat, we're going to have Jonathan review a visualization tool he created. Well, I think we'll do it next week if that's okay, Jonathan. Great. We'll do it just at the beginning as an opening. But Jonathan took that on a while back. I know we've been through this one other time, but this is our real formal lecture on PCA. Again, all these cells will run. I'll put that diamonds CSV file in this directory. Now, where are we going after this? Next week, we'll have a small presentation from Jonathan on how to relate the visualization of eigenfeatures or PCA features to original space features. And it's really powerful to be able to do that when you need to. But then we're also going to go into how do we cycle through models and evaluate them against one another. And I'll have that ready for y'all next week. Okay, I'm going to look at the chat real quick. Hugo, I need to put you in timeout because you've been late to too many classes. And I'm just messing with you. Could you please go over eigenspace a little bit? Yes, Charmin. Again, and Charmin, this is something you're not going to understand all at once. It's what you, my grandmother used to tease me, oh, you're ruminating. What does that mean, Mimi? Because I called her Mimi. So, well, you're sitting there thinking about something you've thought about many times before. How did you know? Well, because I know you think a lot. Basically, ruminate on this. Take a break from it, and then bring it back up and think about it some more. It's like a cow chewing its cud. Digested it the first time, but now it needs to come back up and be chewed and gone back a second time. Now, Minha saying if you're going after explainability rather than being orthogonal, you can go for latent factor analysis. Excellent. And Minha, if you want to prepare a notebook that will explain that to everyone, that would be awesome. I've never had an occasion to be motivated to do that, but I'd love to see a presentation from you on it. And then, okay, so Charmin, with the time we have left, a little bit, and you can come off mute or you can answer me in the chat. Did you kind of understand the concept of how when I multiply one matrix by another matrix, matrix 1 times matrix 2, matrix 2 is acting as a transformation of the information in matrix 1 from one space to a new space. Did that make sense?
Yes, that makes sense because I try to think of it like what happens in linear combination. So it
Excellent.
makes, but the thing is that I just cannot visualize that. Actually, it is very hard for me to actually kind of visualize those PCA components.
Yes.
How does that look like in eigenspace?
So right now, look at we're in hyperspace. You can't visualize it. That's why I was using those other illustrations. So, but if you go through, and this will take some time, and don't feel bad if you don't understand it all at first. Saul Kahn's treatment of linear algebra, and when he goes through principal component analysis, is really good. But again, please don't feel bad if you don't understand it the first time.
Yes.
The point being, what you're doing is you're using some special techniques, and I can't remember the mathematician that discovered them, but you're finding these eigenvectors and eigenvalues such that you can find a matrix that does this perfect decoupling.
Right.
And so, but understanding how to do that in a space that you can visualize, it's not overly hard, but it will take you a little practice. And I suggest doing it by hand on 2-dimensional or 3-dimensional space first. Then you can push the I believe button for hyperspace beyond 3 dimensions. Make sense?
Yes, definitely.
Excellent.
Yes.
Okay,
Thank
let
you.
me you bet. Any questions before we go? I want to give you all a break before mentoring.